Section 3, the sequence component. The sequence object is a purely optional component within an OOP-style test bench. In fact, in part 1 of our published tutorial, we left it out and generated all testing within the driver. In part 2, we added it partly to conform more to UVM style and also to enhance reuse. So in slide 30, this sequence object is the source of an untimed series of transactions sent down to the driver via this mailbox. And it need not be aware of DUT-specific pin names or pin timing. The sequence only deals with data packets. It calls .randomize to randomize the various fields of the packet and then sends them along. So conceivably, a test writer engineer could write a complex test sequence without knowing all the details of the pin level, DUT timing, and pinout. In this section, we'll implement our basic test sequence where the DUT remains powered up, and each transaction applies a different random frequency and mode. In section 6, we'll extend that basic test sequence and put the DUT into power down mode for a number of cycles, and then recover and resume normal filtering operation. And in section 8, we'll see how well the frequency and mode values have been covered as a function of the number of iterations. Slide 32, here's our first look at the sequence class code. It is a parameterized class, and we're using this trials parameter to control the number of loop iterations. It defaults to 16. Before we enter the loop, we're declaring a packet meant for the driver. It's going to be transmitted down to the driver through this mailbox. And then here is the key method within the sequence class. We've given it the UVM-like name body. So it loops for whatever number of trials, and on each pass, we construct a new transmit packet. We increment its tag simply by assigning it the loop iterator. And here's the most important item in this whole task. This is the only place in our OOP test bench where we call the .randomize method. At this point, we have a complete randomized packet. We put it into the mailbox, send it on down to the driver, and then for debug purposes, we write out the real time and any key packet data we want to look at. Here's a part of the transcript. We've just launched the body task of the sequence object, and because these transactions are untimed, everything happens in 0 milliseconds. The tags do get incremented, and we are seeing cyclic random modes with no repetition until all 8 values have been used up. Notice the frequencies do repeat here and there, but very likely they're at different modes. So we do not think it worthwhile to correct that. Let's pause for a quick mental exercise. This is a version of our body task with a deliberate logical error. So let's take a few seconds, see if you can spot the problem. Well, the problem, of course, is that we've only constructed one packet. And every pass through this loop, we're simply assigning new values to that same packet. Only the final set of values will be visible to the driver code that gets the packet. As Chris Spear points out in his classic text, the mailbox doesn't contain the packet objects, only pointers to them, and so we're putting the same pointer into the mailbox 16 times. Here's the solution. We've simply moved the call to the new constructor inside the loop. And now every iteration, we're generating a new packet, it's got its own unique pointer, and that solves the problem. To summarize, we can use this sequence component to maximize reuse. In fact, we could have more than one of them, one for each test interface on a complex analog IP block to conform more to UVM methodology. And in our test bench, we used parameters to control testing details like the number of iterations. And as we'll see, we'll have to up the number of iterations well above 16 to achieve full cross coverage of frequency and mode. We called the body method from within our environment block to run this sequence of untimed tests. And our basic conclusion is that an OOP-style test bench seems quite adequate for an analog IP block of moderate complexity. Of course, you'd want to migrate to a full UVM-style test bench for a larger, more complex SoC with many analog blocks on it. In the next section, we'll descend the test component hierarchy and look in detail at the driver and monitor.